Good morning or good afternoon or good evening or whatever time it is that you're watching this video. I hope you're doing well, staying healthy. This is Miss Spung today. We are talking about properties of logarithms, which are really handy in solving logarithmic equations, simplifying log expressions. So good stuff here. This is 7.5 in our textbook. So let's just jump right in and talk about what are these properties of. So what we're going to be looking at, these basically four properties of logarithms, they have a basis in our properties of exponents. So I'm going to be kind of drawing parallels between what we learned back in, I believe it was chapter 5, and how it relates to our logarithms. And like I said earlier, these properties are going to be used to help us rewrite or simplify expressions and certainly solve equations when we're working with logs. Okay, so our first one is this guy. The log with base x, log base x of x is equal to 1. You might call that some sort of like identity property. And here I'm just going to draw sort of our parallel to this in exponents. Again, this comes from chapter 5. If you want to go back and look at those notes from chapter 5, it was like the first day of chapter 5, section 1 there. So the kind of parallel property of exponents is whenever we raise some number just to the first power, it doesn't change. It still just equals that same number. So this is really just in logarithmic form and in exponential form. This is the same equation, and we would call this a property of logs versus a property of exponents. Okay, so that's probably the simplest one. Let's complicate things a little bit. So here, our next property of logarithms, log base b of x to the a power. So we're raising the number that we're taking the log of, it's being raised to an exponent. Another way to rewrite that is to actually take that exponent and multiply it by the log with the same base of that value. So we can basically move that exponent. I'm just going to circle our exponent and point out that we're putting it in front of the log expression. So this is equivalent to, when we learned about exponents, our power of a power rule, where we are raising some base x to some exponent n, and then actually raising that whole expression to another exponent. So when we have that situation, we can rewrite x to the n to the mth as x to the n times m. That's the exact same thing going on here, just with logs instead. So again, that's our power of a power rule from exponents. All right, next up, these should look pretty familiar as well, at least the ones in exponent form. This relates to our quotient, our power of a quotient, I guess, where we have log base, we'll call it x now, of a quotient, of perhaps a ratio, a over b. Another way to write that is log base x of a minus log base x of b. So notice we've got our numerator minus the denominator there. And of course, really, really crucial, the base is staying the same. We consistently have log base x. So like I said, this relates to our quotient of a power rule, where we might have started with an expression, another ratio like this, x to the n over x to the m. And we can rewrite that, since we have like bases, just like we do in the log expression, we can rewrite that as x to the n minus m power. Okay, so here's our log equivalent. All right, same idea. This time we have a product. So our product exponent rule. Log base x again of a times b, we could rewrite as log base x of a plus log base x of b. So there's our equivalent property in exponential form. So x to the n times x to the m is equal to x to the n plus m. So these are really key properties of logarithms. They're going to help us not only solve equations, but also simplify any equations we're working with so that they're easier for us to go forward with. And I want to make sure you put these in your notes. This stuff, it's from chapter 5, so I would say you could add that if it's helpful for you to understand where this is maybe coming from. But really important is the new stuff, the properties of logarithms. So let's dive in and see how we can apply these properties. Oh, real quick, I forgot about this. A question that I frequently get when we talk about logs, and we'll kind of use this fact today, is what about negatives? What about like negative bases or taking the log of a negative number? And we have this property of negative exponents where we can say x to the negative a is the same as 1 over x to the a. So that actually doesn't work with logs. When we talk about logarithms, the base and the number we're taking the log of always have to be positive. So I'm going to try to link a video right here, or I'll just link it in today's calendar. If you're curious about why that's the case, I will link a video there with a little bit more information. But today we're just going to kind of say the number we're taking the log of and the base will always, always, always be positive. Okay, let's go into an example now. Alrighty. So some types of problems that we'll look at are using some given information. So we are here looking at log base 5 of 2, and we're given that it is approximately 0.4307. Now we want to use that information to approximate the value of log base 5 of 250. So the first important thing, of course, to notice is that we have the same base. That's super key. So the idea is we're going to try to represent log base 5 of 250 so that it in some way uses log base 5 of 2. So we're kind of relying on some of those properties of logs that we were talking about. In particular, I'm thinking I probably want to represent or rewrite log base 5 of 250 as maybe a product. So I might rewrite this as like log base 5 of 2 times 125. That's true, 250 is equal to 2 times 125. Now, why is that useful? Well, I can say, using my property of logarithms then, that this product can be rewritten as log base 5 of 2, remember that's what we were given here, plus log base 5 of 125. And I can evaluate what log base 5 of 125 is as well. Remember, if I were to say rewrite log base 5 of 125 in exponential form, let's just do that off to the side. Let's say some variable, I'm just going to say a, is equal to log base 5 of 125. I can rewrite this equation in exponential form, taking my exponent, excuse me, and my base, 5 to the a power is equal to 125. So that might make it somewhat clear to us. A is going to have to be equal to 3. So my expression, log base 5 of 125, is equal to 3. Now I already knew, based on what this problem gave me, what log base 5 of 2 is supposed to be equal to, or is approximately equal to. I was given here that it's 0.4307. So to evaluate log base 5 of 250, I simply now need to add these two values together. So we'll say that's going to be equal to 3.4307. Okay, so that's one example of using log properties to help us evaluate an expression. Let's look at another example kind of similar to this. All right, so again, we are given that the log base 2 of 3 is approximately 1.585, and we want to use that information to approximate the value of log base 2 of 96. So again, we're going to want to try to rewrite log base 2 of 96 in some way that uses log base 2 of 3. So 96, is that divisible by 3, first of all? That's kind of what I'm wondering. Is 96 equal to 3 times something? It is. Yeah, 3 times 32. So that means I can rewrite log base 2 of 96 as log base 2 of 3 times 32. And again, using the same property of logs that we just used, we can rewrite this as log base 2 of 3 plus log base 2 of 32. From here, we're going to follow kind of the same process. I already know log base 2 of 3. That was given in the problem as about 1.585. Now what about log base 2 of 2? Let's say again that this is equal to some variable. Let's use b. b is equal to log base 2 of 32. So if I want to rewrite this in exponential form, we'll take my base 2, what this is equal to, b as my exponent, and that's supposed to be equal to 32. So 2 to the b power is equal to 32. What is b going to have to be? b is going to be equal to 5. So that means my overall equation looks like 1.585 plus 5. That's what log base 2 of 96 is equal to. So overall, we'll say 6.585. Okay. Let's look at another way to apply these properties. Let's look at a word problem. So we're given the pH of a substance. It's defined as the concentration of hydrogen ions, also written as H+, in moles. It is given by the following formula where the pH is equal to log base 10 of 1 over H+. We want to find the amount of hydrogen in a liter of acid rain that has a pH of 5.5. So of course, if you didn't know already, pH is often the quantity, as it says here, of hydrogen ions, but we also just use it as a scale to tell us how acidic or basic a substance is. So that's why you might have heard of that before. So how do we go about solving this kind of equation? We are trying to find the amount of hydrogen in a liter of acid rain. The amount of hydrogen is this H+, so we're actually solving for H+ here. And we are given the pH. So let's rewrite our equation. We know that the pH is supposed to be equal to log base 10 of 1 over H+. But we know the pH, so let's plug that in. 5.5 is equal to log base 10 of 1 over H+. Okay, so how do we solve for that H+? It's in the denominator of the value we're taking the log of. Well, let's see. Why don't we go ahead, excuse me, and rewrite this so that we have exponential form. So I'm going to rewrite this as 10 to the 5.5 power is equal to 1 over H+. that was not necessarily using properties of logarithms, that step there. That was taking my logarithmic expression and turning it into exponential form. Now, if I'm trying to solve for h plus, well, what if we multiply both sides by h plus? I'll write that in green here. We're multiplying both sides of our equation by h plus. So that's going to look like h plus times 10 to the 5.5 is equal to 1. Okay, so I guess we need to now divide both sides of our equation by 10 to the 5.5 power. 10 to the 5.5 power. And this is definitely one where I would say a calculator is very, very helpful. Because I'm saying here, because 10 to the 5.5 is canceled out on the left, our amount of hydrogen, our H plus, is equal to 1 over 10 to the 5.5 power. Let's plug that into our calculator. You could use your TI-84, you could use your phone. What I get when I plug this in is a whole lot of zeros. 0. Let's see, 0, 0. I have trouble counting all these zeros. I think I have 5 zeros. Is that what I'm saying? 1, 2, 3. Yep. 1, 2, 3, 4, 5. And then 3, 1, 6, 2, 3. I'll call it good there. Now you might also see, if you're plugging this onto, especially into your phone, you might see something like 3.1623. Then you see a little e with a -6 next to it. That's scientific notation, something that we will certainly talk more and more about in future math classes. What this means, though, it's another way of rewriting super tiny or super big numbers. This little e represents times 10, and then the number next to it represents the exponent we're raising 10 to. So really what we're seeing here is 3.1623 times 10 to the -6th power. That's another way of representing all of these zeros before we get to the actual value. Okay, so not a whole lot of hydrogen, apparently, in that liter of acid rain. Looks like that would be our answer. Okay, let's look at other types of examples that we can do with properties of exponents. Okay, so we're asked to solve for x, and we're given an expression that, or an equation, I guess, that has a few log expressions. They all have the same base. That's really handy. We've got a consistent base of 3. So a hint for problems like this is to certainly use properties of logs to help simplify each side so that it's just one log. Okay, so the first thing I might do is take this first piece of my my equation, 2 times log base 3 of x minus 2. I'm going to use what I believe was listed as our second property of logs, which means I'm going to take my number that is being multiplied by that log expression, and I'm going to turn that value into the exponent. So we're going to write this just as log base 3 of x minus 2 squared. So we're taking that 2 and moving it into the exponent's place. Now the rest hasn't changed, so I'm just going to rewrite the rest of the equation out. Okay, now what could I do next? Well, I've got a subtraction sign, so I'm wondering if I could use that quotient idea. I have the same base, so those properties all apply. Let's take my log base 3 of x minus 2 squared minus log base 3 of 6 and rewrite it as one log expression. Log base 3 of x minus 2 squared divided by 6. That's what happens with our subtraction sign. Now, of course, the other side, let's use black there, is still just log base 3 of 150. Again, hasn't changed. Okay, well, now we're taking the same log base of each side. When that's the case, we get to essentially eliminate those logs. We get to say, all right, this means that x minus 2 squared over 6 is equal to 150. Now this is something that we can solve. Maybe I will multiply both sides by 6 to get rid of that denominator. So let's see, we'll end up with an x minus 2 squared. And 150 times 6, well, 15 times 6 is 90. So I guess that's going to be 900. Okay. So we've got kind of a quadratic going on here. Maybe I'll take the square root of both sides. Let's see, what color are we ready for? We'll do red. Square root of both sides to undo that squared. So we're just going to have x minus 2 is equal to what? What is the square root of 900? Positive or negative 30? All right, so we're almost here. We kind of have two cases now. I'm going to write this up here, where x minus 2 could be equal to negative 30, and x minus 2 could be equal to positive 30. So of course, if we add 2 to both sides, we'll get x is equal to negative 28, and x is equal to 32. So are both of those valid answers? This is where I'm going to refer back to what I talked about a few slides back, where the log, the value that is that we're taking the log of, and the base of our log always need to be positive. X is a part of what we're taking the log of. So if I plug in, for example, x is equal to negative 28 here, I'll be taking the log of a negative value. I can't do that. It doesn't work. Again, check out that other video if you're curious as to why. So that means I actually have to eliminate this negative answer. The only valid answer is going to be x is equal to 32. So in general, going forward, if we find a negative value for our answer, we should eliminate that as a possible answer. Let's look at a couple more examples. So 4 times log base 2 of x minus log base 2 of 5 is equal to log base 2 of 125. I kind of want to start this in the same way. Maybe you want to actually pause the video and give this a try yourself. That would be a good idea. But I'll go ahead and work on solving it now. So same idea, 4 times log base 2 of x. I'm going to rewrite this as log base 2 of x to the 4th. Okay, now the rest, of course, of my equation did not change. Log base 2 of 5 is equal to log base 2 of 125. Okay, so same idea. Let's take our difference and turn this into a quotient. So log base 2 of x to the 4th power over 5 is equal to log base 2 of 125. All right, so we've got the same log. We're taking the base, or the base is the same on both sides. So we're ready to say, okay, actually, just x to the 4th over 5 is equal to 125. Okay, so we're kind of in the exact same place as we were before. Let's maybe multiply both sides by 5 to get x to the 4th is equal to 625. Okay, then we want to take the 4th root, perhaps. Maybe I'll write that this is what we did, multiplied both sides by 5. And then we'll take the 4th root. Now, suppose you wanted to plug that into your calculator. Remember, you could always type 625 to the 1/4 power as well. So again, we're looking for some number that multiplies by itself 4 times to get to 625. That's going to be positive or -5. -5 times itself 4 times gets us to 625 as well. But same idea, we actually just want to consider our positive values only. So we would say that x is only equal to +5. Okay, moving right along here. Now we've got log base 6 of x plus log base 6 of x minus 9 is equal to 2. So this is slightly different. We're not going to need to use our quotient idea. We're not going to need to use our product idea. What can we do here? We've got this plus sign. Remember, our plus sign means we can use multiplication. So we'll have x times x minus 9 as the value we're taking the log of. Log base 6 of x times x minus 9. Now we could put all of this in parentheses to sort of show that we're taking the log of this. If that's helpful for you, go for it. That's still just equal to 2. Okay, so I wonder if at this point maybe we should just try to put this into exponential form. Again, taking my base 6, what this expression is equal to as my exponent, and then my value goes here. Okay, again, we're just translating from logarithmic to exponential form here. So 6 squared is equal to x times x minus 9. Well, let's simplify both of those sides. 6 squared, of course, is 36. We'll distribute on the other side to have x squared minus 9x. So another quadratic here. I wonder if we can solve this either using the quadratic formula or maybe factoring. So I'm going to need to subtract 36 from both sides before we look at that. Therefore, we'll have our quadratics that equal to 0, x squared minus 9x minus 36. So does this factor nicely? Remember, what we are asking ourselves when we're trying to figure this out is, are there two numbers that multiply to equal -36 and then add up to equal -9? That's generally the thought process behind factoring. And I believe there are. If I'm thinking about the factors of 36, like obviously there's 6 times 6, or I guess 6 times -6 in this case. That wouldn't add up to -9 though, so we want to keep going. What about, let's see, -12 and +3? -12 and +3, which means our factors would look like x minus 12 and x plus 3. Okay, so we would need to continue solving, meaning we want to set each of those factors equal to 0. So we'll have x is equal to +12 and -3. Same idea though, we need to eliminate that negative value, can't be negative, so x is only equal to 12. Okay, let's do one more. This one will need our calculator, just a heads up, we'll need our calculator next one. All right, now we've got log base 7 of 12 plus log base 7 of 6, and that is equal to x. All right, now we're going to use that same property as we did before. We're going to turn this addition into multiplication. So log base 7 of 12 times 6, that's equal to x. Of course, 12 times 6 is 72, so we can rewrite this as log base 7 of 72 is equal to x. And now we just have a pretty straightforward logarithmic form equation that we can just solve by turning into, turning this into exponential form, or by plugging this into our calculator. Like I said, we're going to need our calculator. Maybe I'll turn this into exponential form just to sort of show why. So again, in exponential form, we'll take the base of our log, 7, take what that expression is equal to, x, and make that our exponent. And 7 to the x is now equal to our final value, 72. So I certainly have trouble thinking of some x that we can raise 7 to get to 72. I don't think that works out well in my brain. So I would certainly plug this into my calculator. Remember, on the calculator, assuming you're using a TI 84 or 89, we would type log. You've got a button for that on the TI 84. On the TI 89, you have to press little diamond and then 7. And then inside the parentheses, we would type 72, the value we're taking the log of, comma, and then 7, the base of the log. And we close those parentheses and press enter. And when I do that on my calculator, I get, let's see, x would be equal to 2.1978. So yeah, I would not have been able to come up with that answer using my brain alone. So thank goodness for our calculators here. Alrighty. So that is properties of logs. They help us reduce the complexity of our problems and make them much easier for us to solve. Thank you for tuning in. I hope you all are doing well. Bye.